Okay, in this example, we have an interaction between two elementary particles. After this interaction happens, an electron and a positron get shot out back to back with equal speeds. A positron has the same mass as an electron. It has the same magnitude of charge, but it's positive. So what we're asking for is what minimum speed must they have when they're 100 femtometers apart in order to be able to escape each other. So they want to be able to get apart from each other. So to do this problem, we're going to think about conservation of energy. What we know is that the final energy must be equal to the initial energy. The final energy will be the final kinetic of the positron plus the final kinetic of the electron plus the electric potential energy between them. And that equals to the initial energy of the positron plus the initial energy of the electron plus the initial electric potential energy between them. So by final, we mean after they have gotten very far apart, after they have escaped. And by the initial, we mean at the beginning when they're 100 femtometers apart. And 100 femtometers is 100 times 10 to the minus 15 meters. So this is our positron, this is our electron. They're moving out back to back, so they're coming out this way. They each have the same speed. And that's the speed they have at 100 femtometers apart, which is going to be called V initial, which we're trying to find out. The distance between them at this initial point is 100 femtometers. So 100 times 10 to the minus 15. What else do we need to figure out? When it says they escape each other, it means they're no longer interacting. They no longer have any electric potential energy. So that means that the distance between them is very far apart. And by very far apart, we mean that the distance between them could be approximated by infinity, which means that the electric potential energy between them is 0. So once they've escaped, they're not interacting anymore, which means there's no electric potential energy. So let's see what we can put in here. Once they've escaped, they've gotten far away, and we want to know the minimum speed. As they escape, the final velocity will go to 0. So that's for each of them, both the positron and the electron. We just established that the final potential energy would be 0 when they've escaped because they are far away, so RF is about equal to infinity, and UEF is about equal to 0. So we know that 0 is going to be equal to the initial kinetic energy of our positron, a half times the mass of the positron times V initial squared, plus the kinetic energy of the electron, a half times the mass of the electron times V initial squared, plus their energy of interaction, so their electric potential energy, K times Q of the electron times Q of the positron, divided by the distance between them. So let's see what we know to put in here. The mass of the positron is the same as the mass of the electron, so a half plus a half gives us a whole, so we get m times VI squared plus K times QE times QP over R initial. So QE is the charge of the electron, it's minus the fundamental charge. Q of the positron is plus E, it's positive of the fundamental charge. So that's minus 1.6 times 10 to the minus 19 coulombs. This one is plus 1.6 times 10 to the minus 19 coulombs. Our initial is our initial separation, 100 times 10 to the minus 15 meters. And mass is the mass of both the positron and the electron. It's 9.11 times 10 to the minus 31 kilograms. So we get m times v initial squared. Bring that to this side, it becomes negative, equals k times qe, which is minus e, times qp, which is e, over r initial. The minuses cancel, and then we'll divide both sides by m, so vi squared equals k e squared over r initial times m. Divide both sides by m there. So then v initial is the square root of k times e squared over m times r initial. Plug our numbers in here, 8.99 times 10 to the 9 for our Coulomb's constant, times 1.6 times 10 to the minus 19 for our charge, that guy is squared, divided divided by the mass, 9.11 times 10 to the minus 31, multiplied by the initial separation, which is 100 femtometers. Don't forget to take the square root of everything, and what we get for the speed is 5.03 times 10 to the 7 meters per second. So when this interaction happens, they're actually shot out pretty quickly. Not faster than the speed of light, but still pretty fast.